Hello, everybody. My name is Ayasi Ljubatic. I'm a research assistant professor at the Department of Synthetic Biology and Immunology at the National Institute of Chemistry, and I'll talk about PyRosetta, RosettaScripts, and RosettaLink. I'll show you a single slide of history on de novo design. I'll show you some Rosetta basic concepts. I'll talk about PyRosetta and RosettaScripts, and then the RosettaLink project at the end. So first, maybe just a little introduction of what Rosetta can do in the end, what it's good for. So it can design proteins de novo, which in my definitions means that you design a new structure and a new sequence. So one of the first example of proteins that did that was Top7. So that was in 2003. And since then, a lot of de novo proteins have been designed, and these top 4, for example, have all been designed with Rosetta, including, TIM barrels, repeat proteins of various shapes, oligomers of various shapes, and then, of course, fibers. So basically, Rosetta is an amazing piece of software that's also has a long history. So it was first released in 2003, and that was written in Fortran. And then in 2005, Rosetta was ported to C++, but it was sort of a mechanical port of Rosetta. And then in 2009, it was rewritten as an object-oriented library, which is sort of the same architecture that it has now. In 2009, PyRosetta was also released, and then in 2011, RosettaScripts was released. And then in 2017, Rosetta 3.7 was released, and then we've switched to weekly releases ever since. And then in 2024, Rosetta becomes source available. So it's not completely open source yet, but you can use it for academic purposes without requiring a license or a login. And that's also the same year the Nobel Prize was awarded for protein design. And here are the links and also the documentation. So the basic class of Rosetta is the pose. The pose is sort of all the information about your system. So how it's connected, what the current conformations are, which residues and which atoms is it composed of. So a pose can be a single chain of protein. It can be a protein and its ligands. For example, here we have some ions as well. It can be a heterodimer, it can also be RNA, or something as big as the whole ribosome if you have enough memory. And the residue type contains information about all the residue names, so you can easily query that, and you can also change the structure, so you can change phi atoms, you can change XYZ positions, and also make mutations. The second most important thing in Rosetta is the energy function. So the energy function takes a set of atoms and calculates an energy. And I won't go into the details. There have been many energy functions. They have a lot of terms, but the latest one to use is beta November 16. There might actually be a newer one right now, but this is sort of the tried and tested. And then Rosetta has several interfaces. One thing you can do is you can run an existing executable, for example, here to just relax, minimize the protein and give it input parameters. Or in the old days, you would have to write a C++ program and compile it and then run it on your PDB. Of course, this is very slow in terms of development time. So a Python API was developed where you can use Rosetta in Python, and this is very user-friendly. And my favorite interface is RosettaScripts, which is a domain language, so basically a specific script in XML format where you can sort of tell Rosetta what to do. And importantly, all interfaces basically call the same C++ code. So for the Rosetta scripts, this is how a Rosetta script look like. You have some things for definition, so score functions, residue selectors, and then you have filters and movers. I'll get to all of this in a second. And then you have this protocol section, which is sort of the main part of the Rosetta XML that tells you what gets run and what not. So here's an example of a mover. So you say, okay, this min mover is a test that I want to do. For example, minimize the residues. And you can give it several parameters. So iterations, minimize the backbone, minimize the side chains. And the RosettaScripts is sort of the best documented part of Rosetta, so I would recommend starting there. We'll share the PDFs of these slides at the end. So the mover is a class that can modify a pose, and it's derived from a mover class. And most of the established tasks you can do in Rosetta are sort of implemented as movers. So the documentation is also here on the link. Here are some examples of movers. So for example, you can redesign proteins, you can do fast design and stuff like that. And here's an example in PyRosetta, how you would call PyRosetta, load it from a pose, define a score function, define what you want your mover to do, apply it to a pose, and then save the pose to a different PDB file. And the important thing is here, I'm gonna connect sort of PyRosetta and RosettaScripts, is that you can either call the movers, basically configure them in code, or you can call a wrapper in PyRosetta that can take part of a mover definition and then configure everything from here. So this is sort of, I think personally, something like this is the best way to use Rosetta or PyRosetta, especially because the XML, the documentation for the XML part for the RosettaScripts is so much better. Here's an example of the packer mover. So for example, we see how the packer changes different side chains here, and then in the protocol it minimizes the backbone a little bit, and then it repacks the side chains once more. Another element of the RosettaScripts are ResidueSelectors. So this is basically language for selecting all the residues that you want to, for example, calculate something with or change. So you have a lot of different ones, including useful by geometry. So you have a layer selector or a secondary structure selector. So a layer selector lets you select only residues that are on the outside, or only residues that are in the core inside of the proteins. And this is super important in design, or it used to be, because it would enable you to lower, you would say in the core I want hydrophobic residues, and on the surface I want hydrophilic residues, and it would lower the amount of residues you would need to design. And there's a link here that you can play with. It leads to a Colab notebook where you can sort of play with residues and cutoffs. And the layer selector works in... the layer selector takes a cutoff of the number of neighbors that the structure has. And it gives you another 2 hyperparameters. It's really nice that the protein MPNN, for example, doesn't need this anymore. It's sort of smart enough to know what's a layer, what's on the boundary, what's on the inside. There's also, for example, a secondary structure selector where you can select all the sheets or all the helices or all the loops in the structure. Then Rosetta also has this concept of filters. So this is the protocol section. This tells you what gets run. So we soft pack the core, we soft pack the boundary, we soft pack the surface, then we do a hard minimalization of only the side chains, then we repack the core once more, and then we say, okay, do we have any very buried unsatisfied hydrogen bonds? And if they are, then the trajectory doesn't continue anymore. But if they are not, then we do the hard packing. So for example, some slow steps. So this saves calculation time. Rosetta has a lot of filters, and people started sort of abusing them a little bit, because if you put confidence 0 here, then the filter always passes, but its value is saved to the pose, so you can use it to get information about poses. Here's an example of various filters that are implemented from geometry filters, kinks in the helices, secondary structure motifs, and stuff like that. So there's a bunch of them. And then one of the newer additions to Rosetta are SimpleMetrics. So instead of using filters to get values, you can use SimpleMetrics to get the values that you want. And they can be cached and more easily saved. So here's an example of the SAP score metric. And you can also do calculations in RosettaScripts with these metrics. Or you can see how many residues are selected, or you can also have metrics that are calculated per each residue, not just for each pose. And here's an example of some other metrics that are included, including a surface accessible, solvent accessible surface area, and root mean square deviation, and sequence recovery. So this is how a mini example, an entire Rosetta XML example looks like. You have, first you define a score function, then you define movers, but these are just definitions. So this does not mean that these things will get run. The only thing that gets executed is what's in the protocol section. So here we first call a mover that minimizes all the side chains. So this is here, and then we call a mover that minimizes the backbone and the side chain. So that would be this one. And now I've prepared a notebook. So I'll try to do a live demo, which is always a little bit tricky. But I will also send around the link to this notebook. So while this is loading, it's going to take a little while to install, but I can answer some of the questions while this is loading. So one of the questions is, can we add cofactors? Yes, you have to specify a separate params file like Daniel already answered, and then you can add a lot of cofactors. Do Rosetta XML and PyRosetta have access to the same functionality, or is one more powerful than the other? They have access in principle to the same functionality. Due to technical reasons, sometimes some movers are only available through the Rosetta XML, but as you saw, you can call Rosetta XML through PyRosetta. So in PyRosetta, you can also get access to everything that you would like. How does Rosetta handle non-protein residues? Will it be able to do the same manipulations to them in a physically plausible way? Yes, so you have to prepare a special params file, and then Rosetta can handle ligands and non-canonical residues. So it is very possible to do that. And this is sort of currently one of the advantages of the normal physics-based Rosetta, because the AI models in the PDB don't have non-canonicals, so it's maybe a little bit more iffy. Although AlphaFold 3 and ligand MPNN can both handle also non-amino acid atoms and residues. Can you share the Google Notebook link here? Yes, I can also share it here if you like to play right now. But I will go through this due to time constraints. I will go through this very quickly. Yeah, that's sort of the downside of installing. Okay, so I'll quickly lead you through the notebook just so that you have a little bit of an idea of what PyRosetta can do. So first, in PyRosetta, you always have to import it, and then you can use it. So for example, you can make a pose out of a sequence. Here we'll just give it a random sequence, and it will just try to make an extended, very non-physical pose. And you can also get information about the pose. So we, for example, here take the second residues, and we see this is a glutamine, and the glutamine is charged. These call-up notebooks are really nice because if you press Ctrl and space, you have code completion, and that helps you program a lot. And also, I guess, large language models know how to read Rosetta a little bit, so you can try those as well. And then one of the tasks you want to do in Rosetta, for example, is minimization. So you have to define a scoring function. Rosetta is very verbose. It gives you all of this output that you can usually, unless there's an error, you can usually sort of ignore it. And these are the weights that we mentioned, and I won't go into more details. But you can get a score of your function, and this score is very bad. So lower is better and negative is the best. So this is a very bad structure because it has here like 5,000 of units. And what you can do is you can run minimization. So you can run it in PyRosetta and then minimize your pose. And of course, we see that the score decreased a little bit, but it's still very high. As I mentioned, you can also call Rosetta, the RosettaScripts from Python. I think this is sort of the best way because you can very succinctly, you can in a very concise way give all the parameters. So here we're defining the same mover and we're minimizing just the side chains. And it takes, the first time it does this, it takes a little time because it's validating the schema. But on the second invocations, the Rosetta XML scripts has no additional overhead. So you can see it modified the side chains a little bit. When you're gonna play with this on your own, if you want to solve these tasks on your own, you can just delete these solutions and then try to sort of solve these tasks. If you want to change and minimize the backbone as well, this is also very easy. And then you can see, for example, that the backbone has moved as well. So the yellow one is the original one, and then the blue one is the backbone minimized one. And then you can also do that in Cartesian coordinates instead of internal coordinates, which will sometimes result in better minimized proteins. And then we come to the Rosetta scripts. So this is the layout, right, that we saw. Here are all the definitions. And then this is what gets run in the protocol itself. And this is a full working PyRosetta example. So this entire script will get run when we call apply here. So both of the movers will get called. So we've minimized the side chains and then we've minimized the backbone. You can also extract just part of the XML script, or you can also just, for example, just use a single mover to configure it. And then we have residue selectors. So residue selectors, I'll show it on an example PDB that's downloading now. And then residue selectors can select buried residues or residues in an alpha helix and stuff like that. So here I'm showing the selected residues. The selected residues are shown with these thick white side chains. So here we're selecting, for example, just chain A with the residue selector. And this is the layer residue selector we talked about. So we can, for example, select just the core residues or just the surface residues, which is very useful in some design tasks. And then residue selectors can also be combined. So you can select chain A and a helix, for example, which would not select the loop in this case. So this is a very powerful way of selecting residues. And here are some tasks that you can solve on your own if you like. For example, just selecting the loop residues or creating layer residues. Then we also have, there's also a very nice application where you can play with the cutoffs, for example, for residue selectors. So blue is surface, green is boundary, and then yellow is core, and then you can sort of tune it to what parts you would like to redesign. Do you want more core? Do you want more interface? Do you want more boundary? And then we have filters. For example, a very useful filter is shape complementarity, which sort of shows you how two protein surfaces interact. And these filters also return a value, and this one is very verbose, but values above 0.6, 0.7 are considered very good. And then we have SAP score, so this is something we covered. This sort of covers the aggregation propensity or the surface, how polar the surface is. And then maybe just to showcase one interface analyzer is a mover that can give you a lot of metrics in an easy format about your interface. So if you're designing, I don't know, binders to a target, you get a lot of metrics about the size, the DDG, and stuff like that. And this is how, for example, a real-world XML file looks like. You have your definitions of functions, your definitions of residue selectors. I'll skip over task operations for now, but then there's a lot of filters and then movers, and then this sort of describes what your script does. So we're minimizing all the side chains, we're analyzing the interface, we're calculating DDG, we're calculating the charge of chain A, we're calculating the exposed hydrophobics, we're calculating another contact surface function. We're calculating very buried and surface buried unsatisfied hydrophobic hydrogen bonds, the SAP score, and then we're seeing if any residues are clashing, and then the shape complementarity. And this you can run everything in the PyRosetta as well. And then you can print and filter on those metrics. And then you have a lot of options of how to do low-level Rosetta manipulation. So for example, if you have a pose, you can easily change its coordinates or change the dihedral angles and twist things. So I won't go into more details here, but you can play with the notebook in the link. So, are there any questions on this part? And Hope, maybe you can let me know if I missed some questions in the chat because I wasn't really reading the chat right now.
I was looking back. I think most of them have been answered.
Okay, cool. Great. Then let's look into the future a little bit, right? Apps. Okay, so now where does that leave us, right? We've got Rosetta, which is an excellent sort of workflow library or like a toolbox. But on the other hand, we have a bunch of we have, and RosettaScripts does all of it, encapsulates all of these tests very nicely. And once you get to know RosettaScripts, it's really an amazing abstraction. It works really, really well. It might have a little bit of a learning curve, but it sort of solves all the problems with if you want to change your workflow, right? In Prosculpt, for example, we can't add, it's more difficult to add different components, change the workflow, while in a RosettaScripts script, it's very easy. So you basically just add an additional line or like maybe move the lines a little bit, and then you can calculate monomers, calculate RMSDs. So it's sort of a really good abstraction. But on the other hand, we have all of the new AI methods, right? So nobody's using PEC rotamers anymore. Everybody's using protein MPNN, and nobody's using like a few people are using like backbone generation in Rosetta or like the Helix builder, because now you've got RF diffusion, Polsky, Collab design, Chai, so you can get your backbones with higher success rates and more variability with the new AI methods. But is there a way to get the best of both worlds, right? So this is sort of one of the reasons we started writing Prosculpt in the first place. But then we're starting to run into problems where we want Prosculpt to do too many things. It gets a little bit harder to modify. So in the future, this is sort of work in progress right now. We're planning to wrap basically any artificial intelligence or like other design tools in a thin Python wrapper. And this Python wrapper will take inputs from a pose and it will also return a pose. So it will sort of be compatible with RosettaScripts. And there's a trick that allows you to write the movers and these wrappers all in Python. So that they can be used in PyRosetta, and then they can be used in RosettaScripts. And the idea is we will call the tools from the command line, so they can be in Dockers, and you don't have to mess with different versions that Bindcraft, that for example Bindcraft needs different CUDA drivers versus Protein MPNN. So you can have each of the tool in their own Docker container. So to write a mover in Python, you basically just have to implement this 1, 2, 3, 4, 5, 6, 7 methods, and then you automatically you can plug into the existing functionality, and you can use this in RosettaScripts, or you can use this in PyRosetta. And this was pioneered by Moritz. So we already have we already have wrappers in Prosculpt that basically call RF diffusion, protein MPNN, Colab. And as we saw in the last session, ProtFlow sort of chose the same approach, where there are also Python wrappers. So maybe there's some opportunity here for standardization. And in the future, we plan to implement the first three that we plan to implement are ligand MPNN, RF diffusion, and Colab fold. So that's the basic. But then it would be very easy to add like bold, chai, ESM fold, alpha fold, Colab design, or RF diffusion tree. And this is how I sort of envision that a Rosetta script will look like. This is a Proscal pre-implementation, just designing just a simple unconditioned mono. So first you would call set up all the paths where your tools are installed. Then, for example, you define an RF diffusion mover, you give it a config and how many designs you want it to have. Then you define a ligand MPNN mover, and you give it the temperature, what parameters you want to meet, and also how many poses it should return. Then you define a Colab fold mover to tell it which models it should run, should it replace the current pose, which type of MSA it should use, and maybe if it's also should calculate some specific RMSDs based on residue selectors, for example. And then you would have filters, right? All the standard Rosetta filters and maybe some new ones. And then in the protocol section, I also envision some changes. First, of course, you call the movers, but then this for each pose tag is a shorthand for a multiple pose mover. So basically it runs a loop for each of your poses. So that here, or RF diffusion, for example, would make 3 backbones. And then for each of those backbones, you would first filter on the backbone level, and then you would call protein MPNN, which also again returns 3 poses. And then for each of those poses, you would run the filters, and then at the end, our Rosetta script returns like a table of all the PDBs and all the metrics that you, SimpleMetrics and movers that you implement here. And actually, a prototype of this for each pose has already been written by Rocco. I have to review it, but I hope it's going to be merged soon. So, as far as closing thoughts go, I think sort of the essential ingredients of perfect workflow library would be that it would have standard Python wrappers, so that you can call this in Python or RosettaScripts or whatever. I think sort of it needs a common representation of a pose, so that all of the movers, all of these wrappers can sort of load and save from the save format. And I think a domain-specific language such as RosettaScripts gives you the most flexibility. Of course, it's possible just to write this in pure Python, but then there's 100 different ways to get to solve the same problem, and then everybody's Python code is a little bit different. But if you have a domain-specific language, this constraint also makes it easier to read other people's scripts, because it forces you into this abstraction, which I think is very good. And with that, yeah, I would like to thank you for your attention, and I'm happy to take questions.
We do have the last question in the chat was where can we keep up with progress, and can anyone contribute?
Yeah, if you want to contribute, just contact us. We haven't made the repo public yet, but we can do that shortly, especially if there is enough interest. Are there any other questions or comments? And oh, maybe just before you go, the next meeting is going to be on February 10th, and it's going to be a detailed tutorial of OVO. So it's going to include on details about how to write plugins. Well, thank you everybody for joining. I hope you learned something useful. And if you have any other questions, you can also reach us by email.